Hello everyone. So in the today's session, we are going to discuss the concept of switching functions in the digital electronics. So first of all, we need to know the concept of a function and how this function is related to the concept of switching. So let me explain you. So in general, suppose if you write a small f of x equal to x square plus 2 So it means that f is a function that is being depending on the variable x. So f is a function which is going to depend on the variable x. That means for each and every value of x you substitute here, you will get different values for this f of x, right? If you substitute x equal to 0, you will get 2 as your answer. If you substitute x equal to 1, you will get 3 as answer. If you substitute x equal to 2, you will get 6 as answer. Like this, for each and every value of x, this f of x will be varying, right? That means f is the function which is totally and completely dependent on the variable x, right? That means this particular function or this particular expression is going to decide the functionality or the behavior of this particular function. Like that, in the Boolean algebra also, we have a special functions where these functions represents the concept of switching in the digital circuits. Okay, the functions which represents the switching mechanism of a digital circuit, we will call it as a switching function. Okay, and remember that the switching functions should be represented always with a capital letters, like this f is equal to a plus b. Just to write an example for switching functions, a plus b. It is also a function. What does it function? What does this mean? This function f is being totally depending on the two variables a and b, right? Suppose if you substitute value of a and value of b, suppose if you substitute value of a equal to 0 and b equal to 1, you will get the answer as 0 plus 1 is 1. If you substitute a equal to 1 and b equal to 0, then you will get answer as 1 again. If you substitute both values are 0, then you will get 0 as your answer. If you substitute both values are 1, then here also you will get value as 1, right? As this is Boolean algebra, where we need to substitute only zeros and ones. It is a binary system. That means in digital circuits, it accepts only binary numbers. It is 0 and 1. That's why I just substituted the values of a comma b in different modules, and I got the substitute results. So this a plus b is nothing but it is a expression which is deciding the functionality of the circuit. So what is the function of the circuit? This a and b is being added with each other. See here, plus is there. That means we are adding this a and b each other. Therefore, this is the function or this is the expression which is related to an adder circuit. Like that, you can decide, right? Until unless you don't know the function, you cannot decide the uh, behavior of a circuit, right? Until unless if I write f is equal to until unless if I write f is equal to a into b, you cannot say that it is an expression given for and what is the equation a into b? It is nothing but it is an AND operation. You cannot say that it is an AND circuit or AND gate. Okay. So if you want to decide the functionality or you want to define the what is the working procedure and what circuit it is, you need to know the function first. This function will decide, this function or this expression will decide the functionality of the circuit. That is nothing but the switching of the circuit, how circuit is being switching for each and every input combination. Then only you can say the name of the circuit. That means the function which specifies or which describes the switching mechanism of a particular circuit, which describes the behavior, is nothing but your switching functions. Okay, how can I define the switching function? Is the function which the function which decides the switching characteristics of a circuit is called as your switching function. Okay, now as I said that this Boolean expression can be Boolean expression can be represented in two different ways. Okay, the switching function is nothing but it is an expression which decides the functionality of the circuit. That means the switching mechanism of the circuit, and these Boolean expressions can be represented in two different ways. Two different ways. What are the two different ways? Is the first one is SOP form and second one is POS form. Okay, SOP form and POS form. What is SOP form? SOP is nothing but sum of product terms. What is POS form? Product of sum terms. Okay, see here, sum of product term, and here second one, product of sum term. Okay, SOP and POS form. These are the two different forms or two different models where a Boolean expression can be represented. Okay, so how can you write the expressions in this form? See, if you find an example here, you will find the example. Here the example is taken as AB plus AC, right? So what is AB? AB in the sense it is nothing but A dot B. It is nothing but A dot B. So it is one product term. When you multiply two literals or two bits, then you can say it as it is an product term. So A into B plus, then what is second term? A into C. So the first product term is AB and the second product term is AC. This is first product term. This is second product term. And these two product terms, what we are doing here, we are doing plus. Plus in the sense it is nothing but addition. It is sum. When you are adding two numbers, you will get the answer as sum. Okay. Therefore, we are doing sum of two product terms. That's why it is an format of S, sum of product terms. So this is an example for SOP. Okay, clear? So we should have product terms like this. P all. Okay. Oh, okay. You may have n number of product terms, and all these product terms should be added with each other. Added with each other. Then you can say this format as the SOP. Okay, this as your SOP. Please remember that the product terms should be summed with each other. Then only it is said that it is an SOP form. Then what is POS form? Same, product of sum terms. First you will have sum terms. See, A plus B is a one sum term. What is sum term? When you add two literals, you will get the sum term. So A plus B is one sum term. Likewise, A plus C is also one sum term. Just I'm writing an example. Just you please follow that. Okay, A plus C is one sum term. These two sum terms are being producted with each other. See here, I am putting dot between them. That means this is one sum term. This is one sum term. We are having two sum terms, and these two sum terms are being producted with each other. Therefore, it is nothing but product of sum terms, right? So this is the representation of POS form. So it's very important. That means we should be able to identify whether the given expression is in the form of SOP or it is in the form of POS. It's our responsibility to learn to identify how the expression is being framed. Okay, remember that SOP is nothing but we will have product terms that are being summed with each other. So this is the example. Okay, and what is POS? We will have some terms and they are being produced with each other. Okay, sum of product terms, product of some terms. It's very important. Please make a note of this. Okay, and now as what I said, sum of product terms. Sum is nothing but we can represent with symbol sigma or summation, right? Likewise in POS, it is we are doing product of some terms. So product which is represented with pi. So please remember that SOP is nothing but it is nothing but it is the summing of product terms. Therefore, it is given the symbol of summation, and in POS it is given the symbol of pi. Why? Because we are producting the we are producting the sum terms, right? Product in the sense it is pi, sum in the sense it is summation. Please remember SOP means summation and POS means pi. Wherever you find pi, Directly you can say that it is an POS expression. Wherever you find sigma or summation, you can directly say it as an SOP expression. Okay, clear? Then we will move to the identification, how we can identify with some more examples, right? Okay, see, if you see here, this is also we have two examples here. So when you observe this first example, this f of, so what is this f of a b c d? F is a function which is entirely depending on the four literals a b c d. If you write a literals like this a b c d, it means that all these four variables or four literals will be made this f to be dependent. That means f is been entirely depending on a as well as b as well as c as well as d. So f is being completely depending on all these four literals, right? So f of a comma b comma c b comma is equal to c a b bar c. It means a into b bar into c. Okay, you can write a dot b as ab also, no problem. A dot b, there is no certain rule to specify dot specially. Okay, please remember that a dot b can be simply written as ab. Okay, if you find ab, it means that a into b. Likewise, if you find a b bar c, a into b bar into c plus b bar d bar means b bar into d bar. Here a bar c d bar means a bar into c into d bar. Okay, see, I am placing dots between them. Okay, if dots is present or not present, it is not considered. So please make a note of this. A into b can be written as ab in general. Okay, so now a into b bar into c, what is this term? We are multiplying three literals, therefore it is one product term. We are multiplying, so it is one product term. Say what is second term? It is also one product term. Why? Because we are multiplying b bar into d bar. Then what is the third term? It is also a product term. We are multiplying a bar into c into d bar. Total we have three product terms. Now see, this product term, this product term, this product term. All these three, what we are doing here, we are doing plus, right? Summing of all these p1 plus p2 plus p3, right? First product term plus second product term plus third product term. Always we are doing plus. That's why it is an expression for of sum of what we are doing here, sum of product terms. So SOP. So this is the example of SOP. You can say it as clearly this expression is your SOP expression. It is nothing but SOP. Okay, likewise, what is this second expression? It is also nothing but f is a function which is completely depending on the all four variables a b c d. So see the first one. What is this term here? A bar plus b plus c. That means it is one sum term. What is second term? B bar plus c plus d bar. It is second sum term. Why? Because we are summing here plus. So sum term. Next, a plus c bar plus d. This is also one sum term. So it is third sum term. And what we are doing here, see here, we don't find any symbol. That means dot will be their default. In default, dot will be there. Here also dot will be there. That means we are multiplying s1 and s2 and s3. So first sum term into second sum term into third sum term into in the sense we are multiplying them. Multiplying means product of what we are doing here, product of some terms. So some terms, product of some terms, therefore it is nothing but POS. This is the pure example of your POS. This is the pure example of SOP. Okay, now I hope you have a clear idea regarding SOP and POS. SOP is nothing but summing of your product terms, summing of your product terms like this. POS means producting of your sum terms, producting of your some terms like this. Okay, it's very very important to identify whether it is an SOP or POS, right? Now then just to be on the line, just to have some Okay then, and now so if you see that in the first case we are just summing all product terms, therefore it is SOP, and we are in the second condition we are producting all the sum terms, therefore it is an POS expression. Okay, now as we know that generally each and every Boolean expression, that means a normal SOP or POS, each and every expression will be existing in two different ways. One is a normal form and the second one is canonical form, or else we can call it as a standard form. Okay, you can call the first one as normal form or else you can call it as a canonical form. That means what I am saying is one SOP expression can exist in two different ways. One is normal form, that means normal SOP, and second one is canonical SOP. Likewise, a POS expression can also exist in two different ways. First one is a normal POS and the second one is a standard POS or canonical POS. Okay, please remember that an expression either SOP or POS can exist in two different ways or two different forms. First one is a normal form, that means a normal SOP or normal POS, and second one is a canonical form. Canonical form or standard form, both are same. Canonical form or standard form, both are same, right? Now now how to differentiate or how to identify the difference between these two, right? So let me explain with an example. Okay, let me explain. Just I will move to the previous slide and then I will explain there. Okay, see here. So you can clearly observe here. See, uh, if you take this as an example, same this as an example. Here, what I have said, f is a function which is entirely depending on all these four variables, right? Now, suppose if an expression is said to be a canonical, please carefully listen. If an expression is said to be canonical, then it should satisfy one condition. What is that condition? What is the condition means? All the literals present in the function, all the literals present in the function must and should exist in each and every term of the expression. Okay, once again I will repeat the condition. All the literals present in the function must and should exist in each and every term of the expression. Okay, see, all the literals in the function means A, B, C, D. All these four literals must and should exist in each and every term of the expression. See here, first term A is existing, B is existing, C is existing. Please don't consider about this bar. Okay, whether it may be a bar one or not complemented. Okay, whether the literal may be in true form or is complemented form, that is not considered here. Whether it is existing or not, that's it. Okay, A, B, C, all three are existing. D is missing here. In the first term, we don't find the literal D. Likewise, when you observe the second condition, second term, B bar, D bar, that means B and D are existing, where A is missing as well as C is missing. Two literals are missing here in second term. When you observe third term, A bar, C, D bar. So A, C, D, B is missing here. That means when I observe the entire expression, I found out that in each and every term, one literal is missing. In each and every term, literals are missing. That means this particular given expression is not a canonical form. Is not a canonical form. It is only a normal form. Okay, it is only a normal form. Why it is not canonical means I found out that in each and every term all the literals are not existing. Okay, as I am having four literals, but I am not having four literals in each and every term. Only three literals are there. Here two is there, here three is there. That means in the left hand side the function is depending on four literals, but in the right hand side the expression consists of only three literals in the expression. That means in each and every term one literal is going on missing. That's why it is not a canonical. It is only a normal form. It is only a normal form. Okay, you can directly say it as it is a normal SOP. Okay, it is SOP basically. It is basically SOP. That too a normal SOP. Okay, it is SOP basically. Already in SOP we have two conditions. One is normal SOP, one is canonical SOP. Among those two, this equation comes under the normal SOP category. Likewise, this is also basically a POS, but in POS we have two conditions: normal POS, standard POS, that is canonical POS, and you need to find which category it belongs to. See here, also F is going to belong depending on four literals A, B, C, D. When you observe the first term, D is missing. When you observe the second term, A is missing. When you observe the third term, B is missing. That means again the condition is not verified here. What is the condition for canonical? All the terms, all the literals should exist in each and every term. But in each and every term, I have found one more literal missing here. That's why it is not a standard form. It is not a canonical form. It is only a normal form. Therefore, it is also a POS equation basically, but it is a normal POS. It is a normal POS. Very, very important concept just to learn how to identify. First thing is you need to identify whether the given expression is SOP or POS, and then again you need to concentrate on whether it is a normal form or canonical form. Okay, already you know it is SOP, but you need to categorize whether this is a normal SOP or canonical SOP. This is expression you know POS form, but you need to know whether it is a normal POS or canonical POS. For canonical POS, we have a condition that each and every term should consist of all the literals. But here D is missing, here AC is missing, and then here B is missing. Therefore, in each and every term, we are finding one literal missing. Therefore, it is not canonical, it is only a normal. Here also, we are finding D is missing, here A is missing, and then here B is missing. So, here also, we are finding bits are missing here, literals. Therefore, it is not a canonical, it is also a normal. Okay. Then the question arises for you, how the canonical form will be. Okay, how canonical form will be. See here, I have let a small example. F of x comma y. F of x comma y. That means f is a function. F is a function which is depending on the two literals x and y. Just a small example. Okay, remember that f of x y nothing but f is a function depending on x as well as y. Now I will let an expression see carefully. Xy bar plus x bar y. Right? So if you see here, this is the first term, and in this first term, x is there, y is there. Both are there. Here also we are having two, x and y. All the literals present here are existing in first term. If you observe second term, here also x is there, y is there. Likewise, all the terms are existing in this term also. Therefore, in each and every term, all the literals are been existing. Therefore, this entire expression is an canonical SOP. Canonical SOP. Right? Is it clear for you? This expression and this expression, you can have a small difference. Here, all the literals are not existing in each and every term. But here, in this condition, each and every term consisting of all the literals. Therefore, it is canonical form and this is a normal form. Okay, right? Then, see, just whatever I have said now, that will be given. See, in standard SOP and POS, just know what I have said, the condition, that condition I have written in this matter just to make a note if you require. This is a standard POS. You can say it as a canonical also. Canonical or standard, both are same. Okay. In standard SOP and standard POS, standard is nothing but you should satisfy one condition. See, what is that condition? Each term of a Boolean expression must contain must contain all the literals that has been included in the Boolean expression. That means in the previous slide I have said no f of something, that f of all the literals that should be existing in each and every term. That term may be with or without bar, that is not a matter here, that should exist. Okay, if the above condition is satisfied, if the above what is above condition, this is a condition, the first point is something but your condition, if this first point is satisfied, then only you can say it as it is a canonical form or standard form. It's very 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 important. Okay, please make a note of this. Okay, see, each term should contain all the literals. This is the main important sentence that you need to write. Each term should contain all the literals that is used in the expression. Then only it is said to be a canonical form or else a standard form. Okay. Now, just I'll move to the next slide. See, here also I took a small example. See here, f of, that means f is a function depending on a, b and c. F is a function depending on a, b and c. But if you see the expression, here only ab is there, here c is missing. In second term, ac is there, here b is missing. As in each and every term, one letter is missing, this is not a canonical form, it is only a normal form. It is only a normal form of SOP. See the explanation I have given here. In the Boolean expression, AB plus AC, the literal C is missing in the first term AB. In first term AB, C is missing. Likewise, in second term AC, B is missing. See, B is missing in the second term AC. That's why it is not a canonical SOP. It is very very important. It is not a canonical SOP. It is not canonical means then it is directly belonging to the normal form. Only we are having two forms. One is normal form, one is canonical form. Now I am saying it is not canonical. That means it directly belongs to the normal form. Okay, normal form. Then how to convert? We need to know how to convert one expression in normal form to canonical form. Okay, we need to know how to convert one form into another form. Okay, now see, I have took the same example what I have said previously, and my task is to convert this normal form into canonical form. Okay, see here, see, y of a comma b comma c. It means that y is a function depending on a, b as well as c. That means all the three literals, all the three should exist in each and every term. But here c is missing and here b is missing. So in each and every term, I found out one literal missing. Therefore, the given question is a normal form. Now my task is to I need to convert this normal form into canonical form. Okay. Please carefully observe how to convert. First of all, you write the question as it is. A B in the sense A dot B. Already I said here A B is nothing but A dot B. A is being multiplied with B plus A is nothing but AB is nothing but A into B. So A is being multiplied with B plus what is AC? A is being multiplied with C. Okay. Now, if I replace or if I multiply this AB with 1, my value will not be changed. If I multiply this AC into 1, then also my value will not be changed. That's what I am doing here. I am multiplying the first term AB with 1 so that my value won't be changed. Likewise, I am multiplying this AC with 1. Here, if you multiply like this, my value won't change. Then the given question will be coming again. Okay, just what I am doing here. I am multiplying here AC with 1 as well as AB with 1. Why? Because AB into 1 is AB, AC into 1 is AC. I will get the same question in my back. Okay. Now, you replace this one with the literal missing literal. What is missing literal here? In AB, C is missing. Therefore, you replace this one with C, where the value of 1 should not be changed. Okay, how can you write 1 in terms of C? Already we have a complementary property as A plus A bar equal to 1. We have a complementary property as A plus A bar equal to 1. Likewise, B plus B bar is equal to 1. C plus C bar equal to 1. It is a universal property. Any literal, it is added to its complement, then you will get 1 as your answer. Likewise, as C is missing, I can replace this 1 with C plus C bar. Can I replace that? Yeah, you can replace. Likewise, in second term, I found out B is missing. Therefore, I can replace this 1 with B plus B bar. Yes, I can substitute here. Okay, what I am doing here, first step I multiplied these two terms with 1 so that my value is not changed. I will get the given question back again. Now, what I have done here, I found out what is the missing literal and I converted this 1 into its own missing literal property. Okay, C plus C bar. Likewise, here B is missing. I substituted 1 with B plus B bar. Then if you simplify this, you will get the question same back again. Now, just I clear the screen. See here, just I multiplied 1 in this step and that 1 is being modified like this. Just by using the property as A plus A bar equal to 1. A plus A bar is equal to 1. By using this property, I have substituted that 1 with the missing literals. Whatever the literals are missing, that I found out, and then I substituted this. Now, we have a distributive property that A into B plus C equal to A into B plus A into C. Consider this AB as a single term A. Now see here, A into B plus C. Likewise, property is there, A into B plus C. Now what you will do, multiply this A with, consider this entire thing as A. Okay, A with B, A into B, A into B in the sense ABC plus ABC bar, ABC bar. Likewise, consider this entire AC as one single term and then start applying distributive law again. AC into B, ACB, ACB or ABC both are same. Again, AC into B bar, that is AB bar C. Just I applied a distributive law and then I distributed the sequence and I got this answer. Now please verify whether any term is been repeating or not. Why? Because if you add A plus A, if you add A plus A, then your answer will be A only. Okay. Why? Because 0 plus 0 is equal to 0, 1 plus 1 equal to 1. Likewise, A plus A is equal to A. Not only 2 A's, if you add n number of A plus A plus A plus A and so on till n number of times, then also you will get answer as A. That's why when I add ABC plus ABC, two same terms are being added. I will get only one time as my answer. ABC plus ABC is equal to ABC. So these two terms are being simplified. Now these two are remaining. Directly write them in your answer. Right? Now this is the step, final step you got. This is the question given. This is the question given, and this is the answer you got. Now your task is to verify whether this is the required one or not. What is required one? The required one is canonical form. What is canonical form? All the terms should exist in each and every term. See here, A is there, B is there, C is there. All the three existing. Okay. Again, A is there, B is there, C is there. All the three existing. Okay. Next again, A is there, B is there, C. So in each and every term, we found all the three literals involving properly. Therefore, the equation what we obtained is a canonical SOP form. It is a canonical SOP form. Like this you need to convert. Okay, next, likewise you need to uh, know how to convert an normal POS to canonical POS. Previously we converted a normal SOP to canonical SOP, and now we will see how to convert a normal POS to canonical POS. Okay, in the previous section, same, here we are having 3, but we don't have 3 here. C is missing. Here we are having B is missing. So it is a normal form that directly we can say. Now in previously we have multiplied with 1 in the first step, but now you need to add zeros so that your value will not be changed. Add 0 for A plus C. Here add A plus B plus 0. Just to add 0 for the both terms so that your value will not be changed in POS. Now we have a property again, complementary property, A into A bar is equal to 0. Can I replace this here? Yeah, you can replace. As A into A bar is 0, B into B bar is 0, C into C bar is 0, D into D bar likewise. Any literal is multiplied with its complement, you will get 0 as your answer. So substitute this 0 in terms of C. Why C? C is missing literal, that's why I am writing in terms of C. C into C bar. Likewise, convert this 0 into B, B into B bar. That is the step. You close the bracket here. This is the step we got. Just I converted this 0 into its own complementary formulas. Right? Now, again we are having distributive law with us. Convert this, add this here, A plus B plus C as your first term, A plus B plus C bar as your second term. Big dot between them. Likewise, distribute AC, A plus C plus B, that is A plus B plus C, A plus C plus B bar, that is A bar plus B bar plus C. So total we got 4 terms. Again observe the same concept, A plus B plus C, A plus B plus C. What is the format here? The previously I said that A plus A plus A plus A and so on n number of times we are getting A as answer. Likewise, A into A into A into A till n number of times you will get answer as A only. Okay, if you multiply A n number of times you will get A as answer. If you add A n number of times, then also you will get A as answer. So by using this formula, now I am converting this A plus B plus C into this A plus B plus C as a single term A plus B plus C. Then we are having two terms remaining. Okay. By simplifying these two, I got this first term. Why? Because A into A equal to A. Likewise, A plus B plus C into A plus B plus C is equal to A plus B plus C. Now, directly copy this term again in the answer and directly copy this term in the answer. Now we got the answer and our task is to verify whether it is a canonical form or not. What is canonical form? All the three should exist each and every term. See here, A is there, B is there, C is there. All the three are involving? Yes, involving. Here A is there, B is there, C is there. Here also involving. Here A is there, B is there, C is there. So in each and every term, we found out that all the three literals A, B, C are involving properly. Therefore, it is an example for your canonical POS. So the question given is normal POS, and by using some properties and methods, we converted into this is a normal form and we converted into canonical form. Okay, like that you need to convert. Okay, it's very important to convert. In the previous slide, see in the previous slide, just what I have said here is I just converted a canonical SOP to normal SOP. Just I multiplied with 1 and that 1 is substituted with, I multiplied 1 with here and I substituted that 1 with A plus A bar equal to 1, a complementary law I used, and by using that complementary law I replaced this with a missing literal, and then I preferred the distributive law and I distributed this, and then I simplified the expression and I got the canonical form. Okay, Likewise, in the next slide, we will get the conversion of a normal POS to canonical POS. Here we need to add 0 in the first step. In the previous column and the previous slide, in the format of SOP, we just multiplied 1, but here we need to add 0 in the first step. And that 0 is been converted as A into A bar equal to 0. Using that property, we convert them and then again apply the distributive law and then finally simplify that. Then you can convert a normal SOP to canonical SOP and a normal POS to canonical POS. Okay, these are the two different and important methods how to convert a normal form into canonical form. Okay, thank you. Hope you understand the session and thank you. Have a nice day.